Okay, well, thank you very much, Julien, and thank you, Barbara and Philippe, for inviting me to talk about this extraterrestrial topic today. I would like to talk about turbulence in planetary cores, on which we don't know much. So don't hesitate interrupting me if things I'm saying are really too extraterrestrial. So why should we care about turbulence in planetary cores to start with? I think there are several reasons. One is that if you care about transport properties like thermal diffusivity, chemical diffusivity, viscosity, magnetic diffusivity, and so on, then probably you should care about turbulence because the effective properties are likely to be orders of magnitude away from those measured in the lab or in ab initio computations. At least that's what we know from what happens in the atmosphere or in the ocean. Typically, effective viscosities are a factor of 1,000, 10,000 larger than the molecular properties for air, for example. And of course, that has some strong impact on things like energy dissipation, which depend on these transport properties, and thermal and chemical mixing, for example. Another reason why we should care about turbulence is that turbulence involves a very large range of spatial and temporal scales, and numerical simulations, which we've seen are very powerful, can't cover that range. Neither do observations. We've seen that they were even more limited, probably in the length scales and time scales they can provide, but as opposed to the numerical ones, they do depend on phenomena which are taking place on these unseen scales, and therefore it's important to know what could be their role for the observations. So what do we know about turbulence? A bad thing is that almost all what we know relates to hydrodynamic turbulence, which is mainly governed by the nonlinear U grad U term in the Navier-Stokes equation. That is, you have the Navier-Stokes equation, the momentum equation. There is in that equation a nonlinear term, the U grad U, if there is strong enough motions and a high enough Reynolds number and so on. And this is at the origin of, for one thing, instabilities very often, but then these instabilities drive to turbulence, like what is shown here with lots of large-scale eddies going to small-scale eddies and so on. And in some sense, one might see that the role of turbulence is somewhat dull. Its role is to transfer energy from the source, some large scale at which energy is injected, often from instabilities which already depend on these non-linear terms, to small scales at which it can be dissipated by viscosity. So that's a very simplified way I can see turbulence and its possible impact for what happens in natural systems. And of course, I think you all know about Kolmogorov's universal view on universal turbulence, which is derived from hydrodynamic turbulence. So it starts with a log E log K diagram, that is a log of the kinetic energy density spectrum as a function of the log of the wave number. That is, you look at scales for eddies which are different size in a sense. And if you inject some energy in that system by some driving, mechanical, thermal convection or something, you expect, in fact, that's Kolmogorov's theory in 1941, that there is some cascade from this injection scale, the one here, to higher wave numbers, smaller length scales, along this line, down to some KD, some wave number where dissipation takes place due to viscosity. This is called the dissipation range. And between the injection scale down to the dissipation range, not much happens except that you're transferring energy from large scales to small scales. And in fact, Kolmogorov's very bright idea was that this takes place with no preferential length scale given. That is, you have a fractal type behavior and no, how to say, sorry, I don't find the word, but whatever. Okay, it's no particular length scale or time scale connected to this. It just cascades from this scale to that one. Okay. What I want to put emphasis on here is that this transition from the inertial range to the dissipation range happens when the Reynolds number is around 1. That is, you have here the Reynolds number, which is the ratio of basically the advection velocity, in other words, the U grad U term, as compared to the viscous time, are about equal. When L, here the length scale, typical length scale, is just taken as being 1 over the wave number. Okay, so this is all really very classical, and big thing that Kolmogorov came up with is that from this simple hypothesis, you get a scaling relationship of what should be the variation of E, the density, energy spectral density, as a function of K, the wave numbers, the famous K minus 5/3 law. In that context, what also is present is that there is here this epsilon. Epsilon is simply the energy flux you give into the system per unit mass. That is, if you give more energy to the system at the injection scale, then you cascade the same way, but at a higher level. And you also will intersect here, go to the dissipation range at a higher wave number, a smaller length scale. Okay, so this is all very classical, but I will try to use this as a guide for some of the developments I'm trying to do, getting closer to planetary core conditions. So what turbulence do we expect in planetary cores? What I've just shown is really quite far from what happens in planetary cores for at least 2 or 3 reasons. One is that usually planets spin around their axis, so there is rotation involved and it plays a strong role. A second one is that many of these planets have a magnetic field, and that also has some impact on the organization of turbulence, we suppose. And also, the turbulence which we are interested in happens in a spherical shell, at least, or some kind of spherical geometry, which also plays a role. So the questions we would like to answer, or at least I will try to ask, is at what lengths and time scales is the turbulence regime dominated by these new ingredients, rotation and the magnetic field? Can we infer the evolution of flow velocity and small-scale magnetic field in these different regimes? How do they cascade? In other words, from large scale to small scales. How much energy is dissipated? This is also quite linked to this question of the cascade, since we have to go all the way to the dissipation range. And what is the balance between viscous and ohmic dissipation in such systems? And finally, which waves can propagate, since we'll see that waves have some role to, or some things to tell us about the different regimes in that type of things. To do that, I'll be introducing what we call with Nathanael Schaeffer TOL regimes, TOL regimes, regime diagrams, which will help us, I hope, try to see what are the different places in this parameter scale, tau being the time scale, characteristic time scale, and L the characteristic length scale. So what are the different regimes which can happen in this range, in these diagrams? If we've used this description in a chapter of the core volume of the Treatise on Geophysics to appear in May 2015. So if you're patient enough, you can have a look on more on the bibliography and the arguments we put forward for these ideas that we're presenting here in the context of the planets, but they're in the context of the Earth's core. The assumptions we have for these regime diagrams is that we start from the idea that turbulence involves a wide range of scales. And time scales tau and length scales L are normally related by the various physical processes that link them. For example, we've seen this morning with Hans-Peter that the diffusion time is related to, of course, for viscosity, for example, to the viscosity, but also to the length scale at which it happens, like tau would be equal to L squared divided by nu in that case. We will see that regime changes occur when these tau of L lines intersect, the ones we will draw from these different phenomena. Dimensionless numbers most often can be written as timescale ratios, and we will use that in this description. And the timescale L at which a dimensionless number is of order 1, like what we've seen for the dissipation range for classical turbulence, is, I think, more important than the value of that number at the integral scale at which we usually evaluate it. And finally, we also assume that turbulent dynamics is controlled by the shortest timescale process, which is something we should debate probably. Okay, so I would like now to try to illustrate these ideas with the simplest diagram we can start with, this Kolmogorov hydrodynamic turbulence A of K diagram I just showed you, but in this different representation. And to make it more planet-like, I've tuned this diagram to the size of Mars core, I hope. I mean, I hope it's not too wrong. So I've taken here the radius for the Mars core of 1,500 kilometers, just to play with that. And this is this TOL diagram I'll be using all over the presentation. So what are we plotting here? Typical time scale from in seconds, from 100 seconds all the way to very long time scales of many years or centuries. As a function of the length scale, you can think of the size, typical size of an eddy, for example, at which this process is taking place, from 1 centimeter times length scale, all the way to the largest scale we can have, which is taken here as the radius of the core, right? In that representation, this famous Kolmogorov law looks something like that. If you think that you are injecting energy at the largest possible scale, which is this TSV. I call it TSV because later on it will be the time derived from circular variation of the magnetic field. So here is something we might have some constraints of. It's a long time. I've taken here completely arbitrarily a time scale of 20 years for mass motions in the core. Then the relation between the kinetic energy and velocity is such that you expect to have this type of cascade down for Kolmogorov's simple cascade all the way to that line. That line, what is it? It's just the one I mentioned before. The L squared divided by nu is the time scale for the diffusion of momentum. In other words, that's where dissipation by viscosity is going to take place when these two lines intersect exactly as in the E of K diagram I showed before. Okay, so this is where the L scale Reynolds number is for the 1. This is where dissipation occurs. I mentioned that this cascade depends on how much energy input you have. And if you put more energy, that is more energy, that means shorter time scales for the largest scales, you will intersect that line at smaller times. And I mentioned that this also means that you have more energy input in the system, which means also more energy dissipation. So if you take that seriously and you multiply this epsilon I had before by the mass of the core, you end up with what is the total dissipation in the core. And then you can mark this line by this power line, the power labels, if you want. This is 1 terawatt for Mars core. This is 1 gigawatt, megawatt, kilowatt, watt. It varies very strongly in here. And depending on where you will intersect this line, will tell you whether you can dissipate a lot or very little, and whether it's compatible with what you expect for a given planet, for example. Okay. So far we haven't progressed much because we haven't put any rotation, any magnetic field, but we're going to do that now. This was the idea of having these diagrams, because now we're going to say, well, there are other time scales which come in this system. In particular, what happens if we add rotation and the fact that we are in a full sphere when we're talking about planetary core. So I just keep the same diagram exactly, but I add now time scales which are related to rotation. There is one time scale which is fairly obvious. It's that Mars spins at about 24 hours, 23 something. So there is here one time, 10 to the 4 seconds, which say that some things which are at shorter times might be behaving differently. Which are at longer time scales might be behaving differently from what we just saw. In particular, basically what we expect is that if you are having motions or things happening at time scales which are shorter than a day, you are in the classical case of Kolmogorov turbulence. You are not influenced by rotation. If you stir your coffee fast enough on Mars, you're not saying that Mars is spinning, right? On the opposite, when timescales are longer than a day, then you are influenced by rotation. And one thing we expect is that you end up with motions which are very much organized by rotation in the form of quasi-geostrophic structures, like columns which are aligned with the axis of rotation, like what there is on this convection picture by Simetev. So at some large timescales, we expect that quasi-geostrophic motions should be present, and many of the dynamos which are being used for planets are showing some quasi-geostrophic motions. There is another line which is drawn here, which I think is interesting, is that, in fact, it doesn't, at some given time scale, length scales, let's take here, well, 10 kilometers. If you start with some eddy 10 kilometer size, which is not a column, it takes quite a while to elongate it to make a column because of rotation. And people have looked at that. In particular, Peter Davidson has shown that the time it takes for a column to increase is, well, the velocity is proportional to 1 over the omega, the rotation scale, times L, the length scale. In other words, it takes some time to go from here, when you start your eddy, to reach the quasi-geostrophic regime. And in fact, that line is the line which discriminates. That is, for a spherical planet, because you want the column to reach from, say, the equator all the way to the core mantle boundary, it takes a very long time if you start with very small columns. Okay? So in that triangle bounded by where dissipation occurs due to viscosity, the day and Rossby, this line which is the time it takes for a column to form, you don't expect really to have quasi-geostrophic motions, but something which is very much elongated in the direction associated with the rotation, but which is not touching the two boundaries. If that's true, then you expect some things to happen for motions in Mars core if there is no magnetic field, but there is rotation like there is in Mars. And I tried to spend a few minutes explaining what's going on here, supposedly. If you allow me to start from the very small scales here, in that regime, we intersect this viscous line that's quite sizable dissipation, like terawatt. For time scales which are below the 1 day, I mentioned that we should expect some 3D normal convection motions happening here. Then we enter some part which is strongly influenced by rotation, which might lead to some inverse cascade, which brings us up to some here quasi-geostrophic motions, which have like 10 to the 6 seconds, in that case, velocities. There is one thing we have not included yet, is that in a full sphere, in fact, motions which are organized in columns are one thing, but you also can have zonal jets, which can be much stronger. And we know from looking at the atmosphere of giant planets like Jupiter here, that you form bands or jets which are very strong, with strong velocities in that direction. In other words, what I'm trying to say here is that in a planet which is behaving a bit like that, in a planetary core behaving like that, you wouldn't expect to have eddies which are very large, because they would be contained in bands which cannot be very large. These bands, these jets on Jupiter, have the property of holding eddies at a size which is inside one of these bands. The red spot, for example, is the largest eddy you can get in one of these bands. So in other words, I then suppose that if you've measured here some kind of very large-scale velocity on Mars, it corresponds to one of these jets which is circling around the planet, and therefore there shouldn't be any eddy dimensions in this gap between the two. But then you can figure out from this that the typical velocity is giving you the scale of the bands at which this happens. This is called the Rhine scale. Basically, the argument is that the inverse cascade is stopped by getting into when the velocity in the jets is equal to the velocity of Rossby waves. And it happens that in a full sphere, this Rossby wave line, propagation line, is the same as the one I've shown before. So in other words, to summarize for Mars, what I'm suggesting here is that you might expect something in which you have zonal jets inside the core of Mars, with a cascade for the eddies, which is from rather small size to very small scales where dissipation will occur. And you can also compute what is the dissipation due to the zonal jets and to the quasi-geostrophic motions on these boundaries at the top and bottom in the Ekman layers. And it turns out that it's rather small as compared to what you get from the normal cascade down to these scales. Okay, 20 minutes already. I have to go to magnetic field, right? So let's try to do that. And then things become a bit more complicated. Because we expect Alphen waves to be present. This is Alphen here. while eddies are the building bricks of hydrodynamic turbulence, the way I've presented it, and the way it's been presented by this community for long times, it is believed that Alphen waves are those of magneto-hydrodynamic turbulence, which are then governed by two different nonlinear terms in the equation, the B grad B term in the Navier-Stokes equation, if you want the Lorentz force, and the B grad U term in the induction equation. So you couple these two equations when you are dealing with Alphen waves, which are waves which you can see as if you have a magnetic field line and you punch it like a guitar chord. It will then propagate along that field line. There is some coupling both the motion, U, and the magnetic field perturbation on that field line. So if that's true, and the velocity of these Alphen waves is proportional to the intensity of the large-scale magnetic field, which is along which these waves propagate. So if this happens, we run into a problem. So here I jump now to the Earth, where we have a bit more constraints, let's say, because we think we have some constraints on this timescale I mentioned, the timescale for secular variation of about 300 years. That's what we derive from magnetic field variations. And I will show in a minute that we also have some constraints on the typical magnetic field inside the core from the observation of torsional oscillations. So we have these two timescales. One, I've translated this intensity of magnetic wave by the timescale of these Alphen waves, which can then propagate. And we have that timescale of about 4 to 5 years or so. There is a big difference between these two timescales, the one for velocity, the one for magnetic field, which is just a translation of the fact that in the Earth, the magnetic energy at large scale is about 4 orders of magnitude larger than the kinetic energy at large scale, which is something that we do not reproduce in numerical models so far. And if we believe in this MHD turbulence scenario, one thing it predicts is that these Alphen waves are equipartition. You get as much kinetic energy as magnetic energy. So at some stage, you expect that the timescales for velocity should merge with the ones of the magnetic field, which then runs into some catastrophe, because if that cascade, as it's predicted, goes all the way down to dissipation, which in that case is magnetic dissipation, which occurs on the magnetic diffusion time line here, you end up with millions of kilowatts, basically, of terawatts, sorry, being dissipated by this type of cascade, which happens where the Lundquist number at the L scale is or the one that's where Alphen waves are dissipated by this, diffusion, magnetic diffusion. So why is it that this doesn't happen? One possibility, the one we favor, is that there is rotation for the Earth. And one thing which we know from Baginski's 70s and which is now demonstrated from observations, in that case you don't get Alphen waves which can freely propagate, because Alphen waves are stopped by rotation at timescales which are shorter, when the timescale of the Alphen waves is longer than rotation, than 1 day. And in fact, what you can get, though, are some particular type of Alphen waves, which are called torsional oscillations. And this is one image of what's been, in fact, recovered by observations, from observations by Nicolas Gillet, Dominique Jo, Alex Fournier, Elisabeth Canet in 2010. From magnetic observations, and Véronique this morning mentioned that it also has a signature in the length of day, which is very convincing. These torsional oscillations are Alphen waves which propagate on field lines, which you can see in the equatorial plane if you want, although it's not the proper image, but which are kind of motions along cylinders aligned with the axis of rotation, which propagate. You see here the propagation from 1955 to 1957, where this cylinder of red color has moved all the way down to the equator of the planet. That's from that we know that the Alphen wave typical time is 4 years or so, which translates because of this relationship between the velocity of Alphen waves and the intensity of the mean field, of the large field, magnetic field, in intensities of about 3-4 millitesla. Okay, so if this really happens, we get a very different scenario in our Towell favorite diagrams. We think we can't get this equipartition anymore. We don't need to have this equipartition. we expect that, in fact, we'll get some kind of, I don't know, some spectrum here in that dynamo regime, which will stop once the velocity field reaches the magnetic diffusion. That's where the L-scale magnetic resonance number is of order 1. And then we still have a very strong magnetic field in the Earth. And so we do expect that this magnetic field inhibits the cascade. We get very little turbulence because of the presence of both rotation and a strong magnetic field, which is something which we also back from lab experiments which do have these two ingredients. In that case, we end up with a very sluggish core with very little dissipation due to viscosity, dissipation due to ohmic dissipation, which is of the order of, you have to read it here, of a few terawatts, which is already quite large. But we have escaped this equipartition catastrophe I mentioned before because of Earth's rotation. So what happens in other planets? I go very rapidly because, one, I'm late, and because I'm probably saying things which are even more fantasy? Yeah, fantasy. I've taken the example of Ganymede, which has a magnetic field, which is rotating rather fast. And when I put numbers which are also very much guessed from the little we know about these planets, is not incompatible with the scenario I just described. We might expect that in Ganymede, the action of both magnetic field and rotation are doing about the same thing as in the Earth. But now if we jump to Venus, could it have exactly the same dynamo as the ones we have for Earth? It's about the same size, same input of heat, possibly. Could it work? This is the same diagram as before for the Earth. The only thing which has changed now are these two lines, the day line, because Venus spins much more slowly, 240 days instead of 24 hours, and this Rossby line, which is now at the higher level. And you see here that if things were exactly the same as in Venus as in the Earth, just because Venus spins much more slowly, we might not expect this, avoid this equipartition scenario. That is, part of the cascade for the magnetic field is penetrating the regime where you would expect 3D motion to be present. In other words, rotation is not any more important in that region. So I don't know how to draw the diagram in that case, but I'm pointing out the fact that we might have this equipartition catastrophe happening in Venus and preventing Venus of having then a very large magnetic field like what we have on Earth. Okay, so probably not. Which doesn't prevent, I mean, if you look at the numbers I've put here, you still have a very small Ekman number at the integral scale, just that we cross in these cascades the day scale at much longer time scales. But do we know really enough about turbulence in magnetostrophic regime, the one I just described, where you have strong rotation and strong magnetic field? Well, probably not. And I would like to finish by just showing some recent results we've obtained in our DTS experiment. So that's only where the experiment comes in, I'm afraid. But some of the ideas I discussed before are very much influenced.
Inspired.
Yes. So this is an experiment in which we have some motions in a liquid sodium shell surrounding an inner sphere which contains a very strong magnet. So we try to have this rotation and magnetic field present and look at what happens. And this is a reconstruction of what the angular velocity field is inside the shell, liquid sodium shell, and the field lines of the magnetic field entrained by this motion when we start from an imposed dipolar field. And the thing we've recently found is that we can have some information about what is a small-scale response, in a sense. That is, what is the effect of motions we cannot measure directly, small-scale turbulent motion, fluctuations, on something which is related to the large scale. In other words, in that case, the magnetic diffusivity, which is the one which plays a role at the integral scale, if you want. And this is something we've just published last week, and with Simon Cabane, our graduate students, and Nathanael Schaeffer again. And what we find is that turbulence reduces magnetic diffusivity in some part of this experiment where the magnetic field and rotation are strongest. That is, I started this talk by saying that in the atmosphere we expect viscosities which are 1,000 times larger than molecular values. In that case, what we find is that magnetic diffusivity can be reduced by like a factor of 1/3. as compared to what is the molecular value for liquid sodium. And in some places, it's increased to values which are higher than that. So in conclusion, I hope you like our towel diagrams. I'm not sure from what I've seen on your faces, but you'll tell me later on, okay?
It's very new.
Should we expect zonal jets in Mars core? That's one of the suggestions I made. I think that rotation limits the dissipation of the dynamo, which is why we can have it work as the way it works in the Earth. For that reason, maybe no magnetic field on Venus because it spins too slowly, at least today. But we need to know a lot more about turbulence in planetary core conditions, really. And we would like to know more, of course, about the internal structures of planets, but I think everybody in this room also would like. Okay, so thank you.